Okay, in order to do my dishes properly, well, I have had to complete the small animal here in the dishwasher. Okay, I had a bowl sitting on top of a stack of dishes in a larger bowl. Okay, just kind of review this. I got water coming in, that's a well-drawn faucet, and I've got soap that I'm going to dispense at some point. Okay? My question is, given volume of this, the volume of this, when should I add soap so that by the time this bowl fills, overflows, fills this bowl, I have equal concentrations of soap in the two bowls? Okay? So, again, fairly simple differential equation, but how are we going to develop it? Okay, well, as usual when we're doing things, we either go from local to global or global to local. We're going to go local, meaning we're going to look at what happens at some intermediate time here, okay, with some variables. Okay, so okay, volumes V1 and V2. This bowl has volume V1. This bowl has volume V2. And water is going to be flowing in at some rate that I'll call R. Okay? In volume per unit of time, right? Units of volume per time. And we'll assume R is constant, although it doesn't have to be. Okay? And it gets even more fun if R isn't constant. You pretty quickly can get the differential equations you can't solve. Okay? Anyhow, we've got the two volumes, right? Okay? So, at any given time, the concentration of soap in the small bowl we'll call is Q1 of T over V1. Okay? Which is the amount of soap in the first bowl. And that'll be Q2 of T over V2, right? Okay. Now we're going to assume that at the instant the water goes in here, it mixes thoroughly, so the water that flows out at time T is going to have concentration Q1 over V1. Same concentration as the water in the bowl. Of course, this concentration is changing, right? So a change in concentration is pouring into this bowl. So this bowl concentration is changing at some rate. Okay? So we want expressions for the rate of change of Q1 of T and Q2 of T. Well, let's just worry about first ball for now. Because if we worry about both balls, we're going to end up with a system of two differential equations, one for Q1, one for Q2. Okay? Well, systems of differential equations are conceptually a little more complicated, but if you know how to do eigenvalues and stuff, they aren't that bad. And the assumptions we make are one level of abstraction higher, but you basically assume an exponential function. Now it's an exponential matrix function, okay? But not an exponential of a matrix, although we get to that too. Okay, so we don't worry too much about that right now. Just want to frame this problem, and we'll come back to the big problem in a little while, like, a month. But we want to get this whole idea in mind, because this whole thing of changing concentrations, okay, mixing problems, is somewhat complicated and conceptually difficult for students in a way that I wouldn't expect, given the lucid explanations I provided at the very beginning. I have no idea why students don't understand this totally, okay? Except that it's kind of, for some reason, a little bit hard to understand. So I want to introduce it early, okay? So let's just look at the first ball, okay? Let's be satisfied with being able to do the concentration of the first ball, okay? Now for simplicity, let's not worry about the time it takes to fill the first bowl. Let's just assume the first bowl is already full when we start, okay? And actually, let's assume the first bowl is full at some time t, okay? And that's when we're going to add soap, okay? That's not when we're going to add soap to accomplish our ultimate goal of equal concentrations, but, okay?
So we're adding soap at more than one time?
Well, we're going to analyze the first bowl, okay? Assuming, and this is pretty easy. It's going to be a very easy application, okay? Assuming it's full at t equals 0. It looks like soup. S-O-O-P, that's how you spell soup, isn't it? Okay.
That's what I was thinking.
Yeah, okay? We're going to add the soap at t equals 0, okay? Now later on we're going to add the soap later, because if we added at t equals 0, this bowl being smaller than this one, no way you're going to end up with equal concentrations. This bowl's going to have a lot less concentration than this one. Almost all the soap is going to end up in this one, if you just have the soap in there initially, because it'll pretty much almost all wash out of here and in here. And you can prove that, we'll worry about that later. Okay, so we analyze the first bowl assuming this, okay? And how much soap? So we're going to add quantity Q naught at t equals 0, no more after that. So what's going to happen? Well, at time t, concentrations Q1 of t, whatever that happens to be. Of course, we already said that, right? There's our concentration. Well, there's the amount of soap. Okay? Concentration, so Q1 of T over V1.
We're learning how to wash dishes.
Water's flowing in at radar. And the solution with concentration Q1 of T over V1 flows out at radar, right? Okay. So what's the rate at which Q1 is changing? Well, this is all symbolic, and in solving any problem, setting up any problem, let's just go to some specific numbers, okay? Might be a little hard to grasp, and this would be a typical thing to do. Now, if you understand flows pretty well, then you might be able to answer that question, okay? But you probably haven't dealt with it. So let's just say, this is bizarre. Shoulder's sore. I got a pneumonia shot in this shoulder yesterday. This one's a little, I mean, just very mildly sore. Every once in a while I move it and I can feel it. Last pneumonia shot I got, I was afraid my arm was going to fall off. Not really, but I usually don't get sore from flu shots. Nothing. I was on powerful blood thinners at the time. That might have had something to do with it. I don't know. That's the only explanation I get. Either that or I was temporarily a wimp but no longer am. Okay, well, there's a concentration thing. A concentration of pneumonia vaccine here now affecting this shoulder. Is that it? Is this a mixing problem? Okay, well, just spontaneous. I just noticed when I raised my arm that this shoulder felt kind of like this one does. Ridiculous. Okay, not a problem. Okay, so we want to go back again in solving the problem. We want to, okay, let's just put some numbers in this and get a feel for what might be going on. Okay, so digression. To get a handle on this thing. Okay, let's suppose this bowl, pretty good sized bowl, bigger than the one I've actually got, is 3 liters. I'm saying this also, so Alexander, you can pick up on what we did, since you didn't come in to hear the original.
And water's flowing.
Okay, so we got 3 liters of water in this bowl. Okay? And it's also got some soap in it. Okay? With .02 liters of soap at some point. Okay? At some time. We don't care what the time is. We'll get an idea of what's happening here, okay? And the rate is, let's say, water's flowing in there at about 6 liters a minute. Okay? Which would be about 0.1 liters per second. Actually, liter per second, since it's less than 1. Okay? Okay, so question then is, how much soap is flowing out of the container per second?